All right, now, let's talk about global warming. Have you heard of this? There's some myths to it, there's no myths. I'm just going to, I don't believe all of it. I'm just going to give you what the book says and what the objectives of the course say, without trying to put my opinions in it. I believe some of it, but I think the studies that are out there, yes, they're proven. I understand that. But we don't see the studies that disprove it, and there are those studies. And I think it gets a little bit political about that. So I don't want to get involved with that. Does that make sense? I'm just going to give you what I'm supposed to do here. All right. So you understand what people are saying on the news and what people are saying on the platform with presidential elections and stuff that they're talking about over there. So I just want to give you the facts and you make your own opinions. Okay? All right, so fossil fuels. You hear about that. Energy naturally made from very old dead plants. All the petroleum and gases you're burning, all the plastic was from these fossil fuels, from the petroleum. And really it all came from old dead plants. That's what it comes from. And it's in the ground for a long time, and decays and stuff, and it turns into this oil. So they're old, millions of years, sometimes, over half a billion years. Well, these fossil fuels contain high levels of carbon. So gas, which is methane, okay, that's our natural gas. I guess some people use gas for their stoves and stuff, right? Liquid, it's called petroleum, and a solid, we have coal. So you've heard these words. I'm trying to, I think you've heard the words all over the place, but I don't think it was ever organizedly taught to you. So I'm trying to do that now so you can make some sense of this. But those are our three. They're all fossil fuels. Natural gas, petroleum, coal. We're looking at gas, solid, liquid. Carbon dioxide is the main byproduct of burning these fossil fuels. And this leads to what they're saying is the greenhouse gas. You're producing a lot of carbon dioxide in the air. So why is this bad? What's happening with this? I should have just left that up here. Let me redraw it. Let me go back to this again. All right. So we have the Earth's atmosphere. And this is what they're talking about, the greenhouse effect. The atmosphere is this Earth's insulation. It's this, cloud. It's this layer of air that's surrounding the Earth. And it insulates us. If we didn't have that there, the sky would just, not the sky, but the stars, where the outer space is then going to be part of us too. Okay? So we have this layer around the Earth that holds in the heat. It insulates it. And the heat comes from the sun's UV light, right? The ultraviolet light, the radiation that comes over it. So it kind of comes in, it can go right through the atmosphere, but it has a hard time leaving. So it stays in there. So it keeps the Earth's average surface temperature about 59 degrees Fahrenheit. Average. I know it's hotter here and stuff, but we're looking at average when you look at North Pole, South Pole and stuff. So without it, the temperature would drop. Does that make sense? Right? You don't have the atmosphere. It's much colder in outer space. You're not going to be able to store that heat here. So the greenhouse gases, there are gases in the atmosphere. Different kinds of gases, they're all there. Water, carbon dioxide, methane, ozone, nitrous oxide, all these different gases that are in that atmosphere. More gases, if we put more gases there, then the atmosphere will get thicker and thicker. That makes sense, right? Which means that if it gets really thick, now keep in mind, the sunlight comes in, heats up the Earth, it has a hard time going out. Some goes out though, otherwise we'll be burned to a crisp, right? Some goes out, but not as fast as it comes in. But if you're going to make that atmosphere thicker and thicker, it's going to be really difficult to get that heat leaving the earth. Does that make sense? Right? So that's how a greenhouse works, if you've seen like in a plant area, where the light could go through this greenhouse that has a lot of windows in it, but the windows act like our atmosphere. Where sunlight can come in, it has a hard time leaving. And if we made this glass, instead of 1 inch thick, into 5 inches thick, the room will get hotter. Same concept. Clear with that? Okay? So there's global warming. Since the Industrial Revolution, that usually, it officially began in 1750 with steamboat engines, that kind of stuff. Even before that, I don't know much about American history, but in the sense of industrial history, but something like that, right? You're building things. But since then, 40% of carbon dioxide was added now to the atmosphere. Since the turn of the century, well, now I got to say which century because I live in both, right? But the turn of the century of 1900, it got even worse. You know, cars were starting to be built. They were starting doing, 1908 or later on, they had planes and stuff. So we started doing other things. So they're going to be burning a lot more fossil fuels. In the 19th century, there's a lot more being burned. They were cutting down trees. Remember how I said that when we give off carbon dioxide, the plants and trees would take up the carbon dioxide. Well, if you don't have plants, then where's all that carbon dioxide going to go? It stays in the air. You see where that comes in? You see this cycle being broken? Well, people say, well, why don't we just plant more trees? Yeah, but the problem is, when the population gets higher and higher, we've got to build more houses. So we're cutting down trees to build houses with the tree material in place of the trees. So where are we going to put the trees? On top of the buildings? You see what I mean? You got to see this whole thing happen. And like I said before, the earth is 70% water. So you only have 30% land. Okay? So we have this greenhouse effect. It's increased heat atmosphere. And they're saying that we're going to get hotter and hotter and hotter. And it'll impact the ecosystems, biodiversity, likelihood of people. What are we going to do? Right? It heats up too much and the icebergs start melting. Well, icebergs are made of water, then the water is going to get higher and higher, and then California is going to disappear, it's going to cover with water. The polar bears and the penguins have no place to have their habitat, they'll die off. You see the big thing they're talking about? Okay? I don't want to talk about the other argument about things of, not against it, but it's, to me it's not all, I wouldn't say it's not true, there's other things, they have to look more into it, there's other things going on. To give you an example, we've had, and you don't have to worry about this, but we've had other times throughout the ages, way before us, caveman time before them, where carbon dioxide levels have been higher than what they are right now, much higher, and yet nothing happened. Does that make sense? They have to do more studies. I can definitely understand where they're going with this, but there's also some other factor that in the past, nothing has happened. And we don't have that information, but we do have the information that nothing has happened. All right? So that's where I lie on that. I agree with it, but they got to do more studies for me to actually buy the whole idea. Is that clear about that? Okay. And I'm just doing that not to tell you what I think, but I want you to use your noggin yourself and ask yourself questions. Okay, I believe that. But what about at this instance? Can you explain that? These are the kinds of questions that you need to ask teachers, parents, other adults, politicians, because there is two sides to every coin, so to say. And you just have to think about that and before you actually pick a side, so to say. And sometimes you're in the middle. I can believe both sides. All right, let's get back to the science part. All right, so that's what's happening over here is the mechanism of global warming, right? Sunlight comes in and creates this. If the atmosphere gets thicker, the heat in the sun is going to go up. Yeah. All right, so that's what's happening with that. It gets too hot in there, okay? And the effects of global warming are big, okay? Like I showed you that all habitats start getting involved and stuff, okay? And then just showing you what happens, less snow on ice on the mountains, and it's just showing you different things, the coral reefs, and I'll explain a little bit about the reaction again. Now, what will happen too is there's acidification of the environment. You're putting more carbon dioxide in the air, watch what happens. Do this reaction again. So look what's going to happen here. If we put too much carbon dioxide in the air, because we're burning too many fossil fuels, right? We're cutting down trees that are taking up the carbon dioxide. That leaves a lot more carbon dioxide in the air. You agree with me about that, what I said? Yes. Which way is reaction going to go? To the switches or to the foam? To the foam. What happens to the amount of hydrogen? Do you see what's happening now? Since we have too much carbon dioxide in the air, we're going to make the air more acidic. Does that make sense? Yes. Okay? So that's what's going to happen over here, this whole reaction. And that's why when there's more hydrogen in the air, the rain is going to take up some of that hydrogen, and now you've got acid rain. All right? And you have this ocean acidification. Now, this is what's going to happen here. I have a video that I'm going to put in with this lecture, and it'll show you what's happening with the ocean, we're making the oceans more acidic. But this, I'm going to show you what's happening here. If you have too much carbon dioxide in the air, the ocean is made of what? Water. So when the carbon dioxide gets in the air, it's going to go into the ocean and do this, right? So now you have acid over here, right? Or hydrogen ions. But what will happen years later, this will also break up too. To hydrogen over here, and something called carbonate over here. So the oceans become very acidic. Are you seeing this now? Okay? But we also have to look at this. Carbonate. Now, there's things in the ocean that use calcium, coral, shells of clams and mussels and oysters and lobster and zooplankton, which is the smallest animals out there that's the bottom of the food chain. Creatures eat that, and people eat, or other creatures eat the bigger fish and so forth. What's going to happen here is that there's calcium in the water that these creatures need to make their hard shells. Just the way an egg is made of calcium. So now this calcium can't go to the animals. Instead, we have a lot more of this than animals. And calcium is then going to be added with the CO3 too, and you will actually make calcium carbonate. Now this calcium carbonate is going to be floating in the water. It becomes a precipitant, meaning it solidifies. You're going to see a lot of this floating on the water. But then what happens to the animals that need the shells? What are going to happen to those shells? They're going to get thinner, or maybe not even be made, because the calcium is being put onto this carbonate. We're going to do an experiment next, I guess on Monday or so, and it's a teacher demonstration. You can do this at home. You can take an egg, put it in vinegar. Let me just answer this. Let me do this first. What was the tricky question?
So if there's more CO2 than there's the H5, CO3, then
Correct. So if there's going to be a lot of this because of our burning fossil fuels, the reaction's going to go this way, which means you're going to make a lot of this and a lot of this. You make a lot of this later on in the ocean, this can be broken down further into another hydrogen ion from there, and carbonate. The carbonate has a -2 charge. It's ready to grab. It's 2 pounds electric. It wants something. Well, it just happens that calcium floating around in the water, that's a positive. So you put these two together, you're going to get calcium carbonate. So now you just used up all the calcium that the other animals need to use. And they can't make their shells. They can't make the coral, because that's made of calcium. So you're not going to have the lobsters, and you're not going to have, the clams and stuff, which are all part of the food chain. Can you visualize what's happening? Okay?
Hi, it's Paul Anderson. I'm sure you're familiar with global warming, how increases in the amount of carbon dioxide is warming the planet, but you may not be familiar with global warming's evil twin, ocean acidification. The cause is the same, increases in the amount of carbon dioxide, but the mechanism is different. Let me show you a demonstration. This is regular distilled water, and I'm going to use a pH meter to measure the pH of regular H2O, and it's going to be right around 7. Now I'm going to take that same distilled water, we're going to put it in a bottle, and we're going to add carbon dioxide to it. We're using a soda stream machine to shoot carbon dioxide in it. It's now just carbonated water. We're going to put it in a glass, and we're going to measure the pH now. I want you to make a prediction of what you think the pH might be. You could even use your finger and point on the screen to where the pH scale is going to be. Let's see how you did. The pH is going to be 3.6. It's really acidic. Let me show you what's going on. So if we take carbon dioxide and water and mix them together, we get carbonic acid. Now that can quickly dissociate and form bicarbonate. What we're doing here is we're losing one of these hydrogen ions, and that can dissociate again and we can form carbonate. We're losing 2 of these hydrogen ions. Now, if we look at the definition for what pH is, pH, remember, is the negative log of the hydrogen ion concentration. What does that mean? The more of this H plus that we have in solution, the lower the pH is going to be, and it's going to be more acidic. If we add more carbon dioxide, more of it's going to move in, and we're going to have more of this hydrogen ion, and we're going to have a lower pH. Now, the levels of each of these can change. Each of these are reversible reactions, so depending on the amount of carbon dioxide, it can move towards the left or it can move towards the right. Why is this a big deal? Well, life exists in this water, and life is regulated by proteins, and proteins require a specific pH. So studies are showing that if we decrease the pH and make it more acidic, organisms are having a decrease in metabolism, and they can have a decrease in their immune response as well. Now, how much of a change in pH are we seeing? If we look at pre-industrial levels, the pH of the oceans was really basic, 8.25. Post-industrialization, it had changed to 8.14. Now, there are going to be regional differences you can see on this map right here. And you might say that's not much of a change in pH, 0.11, but remember this is a log scale. So that represents a 30% change in the pH. What's it going to look like in the future? Well, as we play those models out into the future, By 2100, it could be as low as 7.80. Now, this low pH is going to devastate ecosystems for a different reason. This last carbon compound of the three is carbonate. That combines with calcium to form calcium carbonate. That's what the shell is made up of. That's what the bulk of a coral reef is made up of. And as we change the pH, we can change the level of that carbonate. What determines the concentration of these three? Well, it's going to be the temperature of the ocean water, the alkalinity, but also the pH. And so we can use a Jerome plot to figure out what's going to happen over time. These are log scales of the concentration of these three compounds. The green represents the amount of carbonic acid, the red line represents the amount of bicarbonate, and then the black line represents the amount of carbonate. Remember, that's important for shells. And so if we look at it at acidic levels, carbonic acid is going to dominate. At neutral levels, bicarbonate is going to dominate. And then at basic levels, those that we would find in the ocean, carbonate is going to dominate. But this blue area represents what's going to happen as we change the pH. And as we decrease the pH, you can see what's going on. The carbonate levels are going to drop off and the bicarbonate levels are going to increase. That's because that free hydrogen is competing with the shellfish, really. The free hydrogen is competing with that calcium carbonate to form more bicarbonate. And so now shells can't make their shells. If we look at what could happen over time, this is a pteropod shell at 7.8 pH. It is literally going to dissolve. And so if we look at, for example, coral reefs, they're getting hit with a double whammy. We've got global warming. An increase in the temperature is going to cause them to bleach or kick out all of their algae. I'll talk about that in a different video. But this ocean acidification is going to take that carbonate, and so they can literally not build more of the coral reef. And so these two things work together. What's the good part of global warming and ocean acidification? If there is a silver lining, it's they both have the same cause. It's increases in the amount of carbon dioxide. If we can decrease the amount of carbon dioxide, we can cool off our planet, and we can also slow down this ocean acidification. I wanted to thank Rebecca Blake. She put this out as an idea of a video that I could make. I'm going to make a couple of videos based on this. If you would like to suggest a video, put it in the comments down below or send it to me on social media. That's ocean acidification, and I hope that was helpful.
Experiment that we're doing, or at least one of the demonstrations, is that we're putting an egg, regular egg with a shell, and putting it in vinegar, which is acetic acid. Now, in essence, the acetic acid is going to react to the calcium on the shell. And it's going to remove that calcium to make calcium carbonate. Again, in the egg, this will be, no. We're going to put acetic acid, and you'll get this in here. All right? Just understand that. You'll get this. But it's going, so this right there, it's going to take the calcium from the egg, remove it off of that, and you're going to see this calcium carbonate floating on the water, leaving no calcium, no hard shell on that egg. You get this rubbery egg, but it's not really rubbery. If you ever crack open an egg, you got that film underneath, it's called the corium. That's what's remaining. And that's what happens there. You could also do this with a chicken bone. That's loaded with calcium. So you put a chicken bone in acetic acid, hold it down there for about 3 or 4 days, put something to weight it down so it stays submerged in the acetic acid, the vinegar, right? And then check it 3 or 4 days later. You can take the bone, you can bend it and stuff. And you'll see this foam on the top, that's the calcium carbonate. That just shows you what's happening with this ocean acidification. Questions on that? Yeah. That's what we're afraid of. We don't know how it's going to balance it up if you keep putting carbon dioxide. This is over years and decades, and these are the things that they're finding now with studies. And that's what they're afraid of. They're thinking in the year 2050, we're not going to see certain atoms. So we don't know how it's going to be balanced. The only way to stop balancing it, or start balancing it, is not burning off fossil fuels. Find other ways to not put carbon dioxide in the air. Hold your breath. Sure, I bet you there's a lot of things. I mean, there's a lot of ways that they can do that. How, I'm not too sure. But that's how evolution happens. Is that they start adapting. They lose, like the way that I was talking about the giraffes, right? With the long necks. Right? They're eventually, the ones with the short necks are going to die off. Soon, if this is where it's going to go, let's say 2,000 years from now, well, certain animals are going to die off, and we're going to have, that's what they're talking about, biodiversity. You're having not just one type of frog, you're having 1,000 type of frogs. Diversity. Because they're adapting to certain things through evolution. So yeah, things will die off, things will come back. Okay? So, summary, the properties of water. We talked about cohesion properties. This is the stuff I talked about yesterday. If you weren't here, then this is just the summary part of it. Where we talked about capillary action so that it can go up a tree. Like how does a tree get its water from the soil if it goes up into the leaves? It's because of cohesion properties. All right, and also some surface tension. We talked about high specific heat, the resistance of temperature changes. All right, again, I gave the example of what water has this high specific heat. And you take an iron pot and fill it with water, and you put it on the stove for 2 minutes. You touch that handle of the iron pot, it hurts, right? It's hot. But if you put your finger in the water, it's just warm. So how does the pot get hotter than the water? It's because the water doesn't have this, it can't change its temperature as fast as other things. Does that make sense? You get a question? Did you have a question? Oh, okay. All right, you got a high heat of vaporization, right? A lot of heat needed to evaporate the water. Okay, and we talked about that too. Ice is less dense than water. Remember how I talked about how ice floats, right? Because the habitats for the polar bears and so forth. You put an ice cube in the water, it will float. Okay, and then we talked about it being a great solvent. Right? You put salt in there, it's going to dissolve things. Put sugar in there, it's going to dissolve things. Okay? Further thoughts, why are scientists looking for signs of water on other planets? Life. Yeah, life. We know on Earth, if there's water, because about 70-90% of all organisms are made of water, we know that there's life. So if we could find any signs of water, even if there's Grand Canyons on another planet, because we know that Grand Canyons here in America, that was made by water. So if there was any signs of water on other planets, then there's a possibility that there could be life on other planets. However, that's what we're talking about if we base everything on Earth. Water is our main thing. Maybe on another planet, it's some other thing. Maybe it's methane that does it. We're basing everything off the studies on here on Earth. All right? So we're looking for water on other planets. Okay? Questions about that?